Dear student, in this lesson, we will continue our lesson of solid principles. In the last lesson, we have studied the first principle in the solid principle suite, name, single responsibility principle. Now we will learn the next principle, the open-closed principle. The open-closed principle, OCP, was coined in 1988 by Bertrand Meyer. It says a software artifact should be open for extension but closed for modification. In other words, the behavior of a software artifact ought to be extendable, without having to modify that artifact. Let's have a look at the illustration. OCP ensures that changes shouldn't ripple out dependent classes or objects or modules. This, of course, is the most fundamental reason that we study software architecture. Clearly, if simple extensions to the requirements force massive changes to the software, then the architects of that software system have engaged in a spectacular failure. Most students of software design recognize the OCP as a principle that guides them in the design of classes and modules. But the principle takes on even greater significance when we consider the level of architectural components. This case study will make this clear. Imagine, for a moment, that we have a system that displays a financial summary on a web page. The data on the page is scrollable, and negative numbers are rendered in red. Now imagine that the stakeholders ask that this same information be turned into a report to be printed on a black and white printer. The report should be properly paginated, with appropriate page headers, page footers, and column labels. Negative numbers should be surrounded by parentheses. Clearly, some new code must be written. But how much old code will have to change? A good software architecture would reduce the amount of changed code to the barest minimum. Ideally, zero. How? By properly separating the things that change for different reasons, the single responsibility principle, and then organizing the dependencies between those things properly, the dependency inversion principle. By applying the SRP, we might come up with the data flow view like this figure. Some analysis procedure inspects the financial data and produces reportable data, which is then formatted appropriately by the two reporter processes. The essential insight here is that generating the report involves two separate responsibilities: the calculation of the reported data, and the presentation of that data into a web and printer-friendly form. Having made this separation, we need to organize the source code dependencies to ensure that changes to one of those responsibilities do not cause changes in the other. Also, the new organization should ensure that the behavior can be extended without undue modification. We accomplish this by partitioning the processes into classes, and separating those classes into components, as shown by the double lines in the following diagram. In this figure, the component at the upper left is the controller. At the upper right, we have the interactor. At the lower right, there is the database. Finally, at the lower left, there are four components that represent the presenters and the views. Classes marked with our interfaces, those marked with our data structures. Open arrowheads are using relationships. Closed arrowheads are implements or inheritance relationships. The first thing to notice is that all the dependencies are source code dependencies. An arrow pointing from Class A to Class B means that the source code of Class A mentions the name of Class B, but Class B mentions nothing about Class A. Thus, in the figure, Financial Data Mapper knows about Financial Data G2.
The next thing to notice is that each double line is crossed in one direction only. This means that all component relationships are unidirectional, as shown in the component graph in the figure. These arrows point toward the components that we want to protect from change. Let me say that again. If component A should be protected from changes in component B, then component B should depend on component A. We want to protect the controller from changes in the presenters. We want to protect the presenters from changes in the views. We want to protect the interactor from changes in, well, anything. The interactor is in the position that best conforms to the OCP. Changes to the database, or the controller, or the presenters, or the views, will have no impact on the interactor. This is how the OCP works at the architectural level. Architect separate functionality based on how, why, and when it changes, and then organize that separated functionality into a hierarchy of components. Higher-level components in that hierarchy are protected from the changes made to lower-level components. The OCP is one of the driving forces behind the architecture of systems. The goal is to make the system easy to extend without incurring a high impact of change. This goal is accomplished by partitioning the system into components, and arranging those components into a dependency hierarchy that protects higher-level components from changes in lower-level components. System components, classes, modules, functions, should be open for extension but closed for modification. That is, you should be able to extend the functionality of a component without changing its existing source code. This can be achieved through inheritance, using interfaces, or design patterns like the strategy pattern, e.g., instead of modifying a class directly to add new functionality, you can extend it through inheritance. Let's have a look at implementing sorting algorithms by strategy design pattern to ensure OCP. Now, your turn, students. Please gives one case of OCP principle.